This presentation was originally delivered at Northern Illinois University in the spring of 2015 as part of the Presidential Teaching Professor Seminars. It's called Pedagogical Reboot, Teaching How to Learn About Technology. Looking back over my professional career as both a scholar and a teacher, you can see that my work really tracks the development of the web. I began writing code in the early 1990s and have developed my skills and interests as a researcher and practitioner, along with advancements in the technology and opportunities of the internet. But I am admittedly a digital immigrant. I did not grow up with this technology. To put this in perspective, I learned to type not on a computer keyboard, but a manual typewriter, albeit not a typewriter as cool and interesting as the one you see here. My students, by contrast, have grown up with computers, the internet, and mobile devices. They are what Mark Prensky calls digital natives. Here's how Prensky defines this term in a rather well-known article from 2001. Today's students, he writes, K through college, represent the first generations to grow up with this new technology. They have spent their entire lives surrounded by and using computers, video games, digital music players, video cams, cell phones, and all the other toys and tools of the digital age. Despite being immersed in all things digital, the technology skills and abilities of this generation is still significantly underdeveloped. I see this in my own students, and it is confirmed by the empirical data. A 2015 study conducted by the Educational Testing Service, the organization that supplies us with the GRE and the TOEFL exams, found that U.S. students had relatively weak skills in literacy, numeracy, and problem solving with technology compared to their international peers. In fact, in the area of problem solving in technology-rich environments, U.S. students currently rank 18th in the world. The way we have typically responded to this challenge is to build into our curriculum efforts to educate students in the use of technology. We aim to teach our students how to use the tools that are available to them, whether that be the internet for conducting research, cloud storage for collaboration, or a particular software application like Photoshop for digital imaging processing. This approach to technology education seems to address what is needed most, teaching students how to use the technology that has and will continue to be a fundamental component of their personal and their professional lives. This effort, however, is misguided, and instead of solving the problem, it might actually be making things worse. So what I want to do today is the following. First, demonstrate the problems and potential pitfalls with this particular approach to teaching technology. Educating students in what are arguably the industry standard tools might appear to be the most expedient way to address the problems of digital literacy. But such an effort is, I argue, not only inefficient, but ineffectual. Second, and in response to this, I will propose a different model of technology pedagogy, a method of education that does not simply teach students about technology, but teaches them how to learn about technology. Although this shift in focus is rather subtle, the effect it has on students and their future can be potentially astronomical. So first, let's talk about the wrong way to do things. Teaching students to use the devices and applications that are available to them appears to be the right solution to the challenge of digital literacy, but this effort has at least three problems. It is expensive for both institutions and individuals. The skills and knowledge it cultivates are perishable, and finally, it contributes to a perception of technology as a kind of magic. So first, instruction that is committed to a specific device, platform, or application is expensive for both students and the institution. In my department, for example, we teach students to use the industry standard tools available in the Adobe Creative Suite. This includes applications like Photoshop and Illustrator for digital imaging, Dreamweaver and Flash for web content development, InDesign for page layout in print and digital journalism, and Premiere and After Effects for video and filmmaking. These are undoubtedly powerful tools for creating digital media, and helping students to become proficient with them seems to be the most important pedagogical objective. But these tools are expensive. even with the available educational discounts. A subscription to the Adobe Creative Cloud is currently at $34 per month per user or $299 per year per device. So let's use the per device cost. If a department wants to make the Creative Cloud available to students in 2 computer labs with 24 computers per lab, the cost per year of that implementation will be $14,352 per year. Additionally, if students want to access these tools on their own devices outside the class, they will need their own subscription to the Creative Cloud. The cost of this is $20 per month. Now, this might not sound like a lot, but this is a kind of new revolving fee that would need to be added to the already burdensome list of fees that our students have to contend with already. Second, the knowledge and skill set that is developed by teaching specific hardware devices or software applications is perishable. As long as the device or application remains in play, the technical ability we impart to our students remains useful and important. But applications, platforms, and devices change, and they change at an ever-increasing pace. Perhaps the best illustration of this comes with the computer itself. This is ENIAC, the first electronic general-purpose computer. It filled a 50-foot-long basement in a building on the campus of the University of Pennsylvania, and it weighed 30 tons. Next to it here, you see ENIAC on a chip, which recreates the original ENIAC computer on a chip of silicon not much larger than your fingernail. So in just 50 years, we went from a massive 30-ton machine to something the size and the weight of a quarter. Similar changes, although not as dramatic perhaps, occur with our devices and applications. At one time, mobile computing was focused on this object, the Palm Pilot. And learning how to use and develop applications for this hardware was the name of the game. Just 5 years ago, Second Life was considered the next big thing in higher education. And universities not only sought to develop a presence in this virtual world, but offered instruction in its use and its implementation. Finally, and probably my favorite example, we have Adobe's Cold Fusion. About 12 years ago, Cold Fusion was considered to be the future of the web, offering designers a robust platform for rapid application development. Today, Cold Fusion is considered a legacy system, replaced by things like Ruby on Rails, Cake PHP, and the Zend framework. Had I decided to teach my students Cold Fusion, that knowledge would have had a relatively short shelf life, achieving obsolescence in just over a decade. Third, devices and applications are intentionally opaque. The hardware is placed inside increasingly sleek containers, and the software sits behind user-friendly interfaces that are designed to hide the inner workings of the mechanism. For this reason, our digital natives often have no idea how these things work. This means that many of them relate to their technology as a kind of magical object. They type an incantation on the keyboard, hit return, and just expect everything to work. And when it doesn't, they will try anything to coax the machine to do their bidding. In teaching to the device or the application, we do nothing to demystify this way of thinking. In fact, we often facilitate it by focusing our instruction on the rituals of use, things like step-by-step directions that need to be executed in a precise sequence and manner in order to get the device or the application to fulfill our wishes. Consequently, when we focus our attention on specific devices and applications, we run into problems. This mode of technology education is expensive. It imparts skills and knowledge that have a relatively short shelf life, and it contributes to a magical way of thinking that puts technology in control. So there is, I believe, a better way to do things. This alternative approach to technology education does not focus attention on specific devices and applications. Instead, it cultivates the general skills and knowledge to be able to learn about and deal with technology, irrespective of the device or the application. This alternative, which I describe as teaching how to learn about technology, involves at least 3 related efforts. First, demystifying technology. Coding across the curriculum, second. And finally, a commitment to free and open source software solutions. So first, demystifying technology. One of the assumptions we often make about our students is that they already understand the technology that has surrounded them their entire lives. This assumption is dangerously incorrect. My students, although having grown up with the internet and using it virtually every day, have no idea where this technology came from or how it operates. For them, it is magical. We therefore need to actively work to demystify our technology. In my own classroom, this effort involves 3 initiatives. First, we spend a good deal of time investigating the history of computing. The computer and the internet come into being at a particular time, and their development and implementation have been shaped by the social, political, and intellectual context. I want my students to understand and appreciate this history and the role it plays in structuring the current state and future possibilities of information and communication technology. Second, we examine the basic operations of both hardware and software in an effort to understand what goes on inside the magic box or over the network. The goal here is not to turn every student into a computer specialist, but to cultivate the general knowledge that is accessible to every student, irrespective of their interests or major. When a student understands the basic operations of their tools, they no longer treat them as magical objects. They take control of their technology. Third, and actually this leads to the second main point. We need to teach code, and we need to make it available to all students. In other words, we need to teach code across the curriculum and not just in 1 or 2 dedicated disciplines. There are 2 reasons for this. First, learning to code is a non-perishable skill, or at least a skill set with a longer shelf life. Unlike mastering the steps for manipulating a particular software application, writing code is a fully generalizable technology skill that can scale and adapt to changes in technology. Like writing, mastering code is a kind of general knowledge skill that applies to every endeavor and extends across all disciplines and majors. In fact, not learning how to code at this particular point in time would be like deciding not to learn to write during the era of print media. Second, code provides students with control over their technology. In manipulating the computer and making it do exactly what you want it to do, students develop not only the skill to take control of their future, but the confidence to deal with technology irrespective of the specific device or application. I think the science fiction writer Cory Doctorow explains this quite eloquently in the book Little Brother. If you've never programmed the computer, the protagonist says, you should. There is nothing like it in the whole world. When you program a computer, it does exactly what you tell it to do. A computer is the most complicated machine you'll ever use. It's made of billions of micro-miniaturized transistors that can be configured to run any program you can imagine. But when you sit down at the keyboard and write a line of code, those transistors do what you tell them to. Computers can control you or they can lighten your work. If you want to be in charge of your machines, you have to learn to write code. Finally, I advocate using free and open source solutions as much as possible. And again, I do so for 2 reasons. First, free and open source software, or FOSS, is free. It is available to institutions and end users without cost. Instead of purchasing a subscription to Photoshop, for instance, we can commit to using GIMP, a FOSS alternative. This application can be installed in university computer labs and used by students outside the classroom without subscriptions, fees, or other expenses. And GIMP, which I use in my own classroom, does virtually everything you can do with Photoshop. The same is true with other applications. Instead of teaching students Dreamweaver, for example, we can engage them in coding HTML and CSS using free and open source alternatives like Notepad++. This approach has the additional advantage that it prepares students for opportunities after graduation. There are no jobs for Dreamweaver programmers. In fact, that title doesn't even exist. But there are plenty of opportunities for individuals who know and can write HTML and CSS. Obviously, not every commercial application has an open source alternative, but many of them do. And if they exist, we should leverage the opportunity. Second, FOSS is open source. That means the underlying code of the application is not hidden or inaccessible. End users not only can examine the code, but more importantly, they can alter it, either to improve the application or build a custom implementation. This not only encourages innovation, but offers unique educational opportunities for both students and instructors. When you can pop the hood on an application and observe and even alter its behavior, it is you and not the application that is in the driver's seat. So where does this leave us? Let me end with just a few concluding thoughts. There is a need to teach digital literacy, especially at this particular time. In a study from 2012, the British Royal Academy found that the so-called digital natives actually have little to no knowledge of the technology that surrounds them. Digital literacy, they argue, does need to be taught. Young people have usually acquired some knowledge of computer systems, but their knowledge is patchy. The idea that teaching this is unnecessary because of the sheer ubiquity of technology that surrounds young people as they are growing up should be treated with great caution. Like Marshall McLuhan's fish that cannot perceive the water in which it lives, our students know very little about the technologies in which they are immersed. This means that teaching digital literacy is not optional. It is a pressing need. But the way we have addressed this need, teaching technology by focusing our attention on applications and devices, is not the best solution. In fact, instead of addressing the problem, this approach often contributes to it. It is expensive for both institutions and individuals. It imparts knowledge and skills that are often obsolete just a few years after graduation, and it does little or nothing to demystify what seems like magic. To counteract this, I'm suggesting a change in course, what I call a reboot in pedagogy. This alternative approach to teaching technology does not focus attention on specific devices and expensive applications, but seeks to develop the knowledge and skills that will be necessary for lifelong success in an increasing technological world. This reboot involves at least 3 initiatives. First, an active effort to demystify technology. Second, teaching code across the curriculum. And third, a commitment to sourcing, using, and improving free and open source software and hardware solutions. This is the approach I've followed in my own classroom, and it is, I believe, the method of technology education that has the best chance of preparing students for lifelong success.